Hi class, Miss Dean here. Today we're going to start with Unit 1, Target 1 notes. For this you'll need your unit packet open to page 3. Take a look at the list of terms needed to know for this unit. You should be familiar with force and net force from the online activity yesterday. The learning target we're focusing on today is target number 1. I can analyze situations where the net force is 0 and determine individual forces acting on an object and can draw or calculate the resultant of 2 or more vector quantities. So we'll start with defining force. Force is abbreviated with a capital F. A force is a push or a pull acting on an object. A force is needed to change an object's state of motion. State of motion just means that the object is either at rest or moving uniformly along a straight line path. A force is necessary to start something from rest. A force is necessary to increase the speed of an object, to make an object turn, or to cause an object to stop. A force is not necessary to keep an object moving that's already moving uniformly along a straight line path. And finally, a force is measured in a unit called newtons, which is abbreviated with a capital N. Next up is net force, which is abbreviated sigma F. This sigma sign means sum, and as you saw yesterday in the online activity, the net force just means the total or the combination of all forces acting on an object at once. This next sentence is missing from your notes. You'll need to add it in. When a non-zero net force acts on an object, it changes the object's motion. I put these two pictures up from your online lab yesterday, and you'll notice here we have a net force of 0. There are equal forces pulling on the object to the left and to the right. They cancel each other out, so you have a 0 net force. What this sentence is talking about, when a non-zero net force acts on an object, it changes the object's motion. It's referring to a situation like this picture, where you have forces acting on the object in both directions, but they don't cancel each other out. There is a non-zero net force, and as a result, you can see that the cart has moved to the right. The net force acting on an object depends on the magnitude and direction of all of the forces acting on that object. Magnitude means the size or the amount with appropriate units. Hopefully you were able to come up with 2 examples of states of motion where the net force is equal to 0. First is when an object's at rest, similar to what you saw in this example. And then another example of a state of motion where the net force is equal to 0 is when an object is moving in a straight line path at a constant speed. If you remember from our definition, force is not necessary to keep an object moving if it's already moving in a straight line path at a constant speed. A scaffolding, like pictured in your notes, is a useful example when we're doing net forces. It's useful because there are several forces acting on it at once. First, you've got 2 forces of tension acting in the up direction. Tension would be like a stretching force, usually from a spring or a rope or a cable. And then you also have downward forces due to gravity, the weight of the painters, as well as the weight of the scaffolding itself. Since we're going to assume that the scaffold is at rest, then we can figure out what the net force is acting on the scaffolding. You guessed it, the net force is 0 newtons. In order to calculate this mathematically, we need to attribute signs, positive and negative signs, to the upward force and the downward force. What makes the most sense, especially if you think about it in terms of graphing coordinates, is that the upward forces would be given a positive sign and the downward forces would be given a negative sign. Well, what about if the forces are acting to the left and to the right? What sign should we attribute for each of those? Again, you can think of graphing, and forces to the left should be given a negative sign, and forces to the right should be given a positive sign. Now we can use these to help calculate the net force. Remember that it's dependent on magnitude, that means the size or the amount of force, and the direction of the applied force. This first example in your chart shows that you've got two forces, both acting to the right, one with a magnitude of 5 newtons and one with a magnitude of 10. So take a minute and draw in the net force that would be acting on that object. What about this situation? Again, you have a force of 5 newtons and a force of 10 newtons, but instead of acting in the same direction, they're acting in opposite directions. What would the net force be in this case? This time, you've got 5 newtons acting to the left and 5 newtons acting to the right. What is your net force acting on the object? Zero newtons. All right, if you flip over to the top of page 4, you've got an example to try. A staging that weighs 300 newtons supports two painters, one who's 350 newtons and the other is 200 newtons. The tension in the left rope is 500 newtons. What is the tension in the right rope? You're going to want to start by labeling all the parts that you know. We heard that the staging itself weighs 300 newtons. It's supporting two painters, one that's 350 newtons and one that's 200 newtons. It also said that the tension in the left rope is 500 newtons. Now, we want to make sure that we've applied appropriate signs. We said anything in the up direction is positive, and anything in the down direction is negative. Now you're trying to solve for the tension in the right rope. We know that the net force is equal to 0. So we need to set up an equation that shows the net force, the sum of all of these forces, is equal to 0. Take a look at the equation. I put the total force, 0, and set it equal to all of the downward forces plus the upward force plus our unknown. Now all you need to do is solve for the unknown, which is the tension in the right rope. Pause here and take a minute to try the two net force equals 0 scenarios in your packet. Let's take a look at the stationary example first. Two kids are pushing on a crate, but the crate doesn't move. Since it's not moving, another way to say that is the crate is at rest, we know the net force has to be 0. The bottom part of this question asks, what is the force of friction between the crate and the floor? We can set that up by thinking of it in a similar fashion to the scaffolding problem. Here's our crate. We have two children pushing on it in the same direction. One pushes with 150 newtons, one pushes with 180 newtons, yet the crate is at rest. Since it's at rest, something must be acting in the opposite direction with an equal magnitude. We know that this must be the force of friction. Using the equation, solve for the force of friction. Now check out the constant speed example. Again, we've got kids pushing on a crate, they're pushing in the same direction, and the crate is sliding at a constant speed. Ooh, constant speed. That should be a hint to you that we have uniform straight line motion. Again, we've got a net force equals 0 case. We can solve it the same way as our previous example. Here's our crate. We have 2 children pushing on it, one with 155 newtons of force and one with 187 newtons of force. And we need to solve for the force acting in the opposite direction. Check your answers. How did you do? And notice that both of these have a negative sign. The way that I drew it, the forces were acting to the left, so they should have a negative sign. If you drew yours in the opposite direction, they should have positive signs, but your negative signs should be in these spots.